Hello, today we're going to look at nuclear spin and how it contributes to the nuclear potential. First, let's consider atomic physics and electrons in an atom. We know that there are 4 quantum numbers for each electron. They are the principal quantum number n, the orbital or the angular momentum quantum number L, the magnetic quantum number m, and the spin quantum number s. And the values that these can take are that the principal quantum number is always an integer, and it goes from 1, 2, 3 and so on. The orbital angular momentum quantum number goes from 0 up to n minus 1. And it is that which gives us the so-called S, D, P and F levels and so on. The S level is L equals 0. The P level is L equals 1. The D level is L equals 2 and the F level is L equals 3. So those are it's the orbital angular momentum that gives us those values. The magnetic quantum number goes all the way from minus L up to 0 and then up to plus L. Again, always in steps of 1. You can never have a fraction. And the value of spin, you can write it either up and down, those are 2 values, sometimes written as plus a half and minus a half, or more accurately plus a half h bar and minus a half h bar. And why do we do that? Because if these are the 2 values of spin, a half h bar, this is 0, and minus a half h bar, you can see that the interval between the 2 is h bar. And this is the whole principle of quantum physics, that you cannot move continuously. In quantum physics, things always move in units of h bar, quantized units, quantized chunks of h bar. And consequently, if you go from plus a half to minus a half, you've moved in an interval of 1 h bar. Now, similar quantum numbers apply to protons and neutrons in the nucleus. And today we're particularly going to be looking at the orbital angular momentum and the spin angular momentum. Now, these 2 concepts can be understood classically very easily. They are the Earth going around the Sun. So here's the Earth, here's the Sun, obviously not to scale. And the idea is that the Earth goes round the Sun, and the going round the Sun is what produces the orbital angular momentum. So orbital is associated with the orbit, but the Earth also spins on its own axis. So this is the spin. So as far as the Earth would be concerned, this would be the L term, the orbital angular momentum, and this would be the spin term, the spin angular momentum. And what we say is that that is our classical analogy, and we can understand that as far as an electron is concerned. Now, this is the nucleus, this is the electron is orbiting the nucleus, so that's where the orbital angular momentum comes from, and the electron spins on its own axis is what we classically say, and that's the spin angular momentum. Well, as I've said before, classical analogies are all very well, but there comes a point where they don't work anymore. For a start, the electron can't spin on its own axis because it doesn't have structure to enable it to do so. If you've got an axis, it means you've got structure. There is no structure in an electron. So actually, orbital angular momentum and spin angular momentum are quantum concepts. They actually don't have classical equivalents. But we can use this as an analogy just to get a rough idea of what we're talking about. Now, neutrons and protons in the nucleus have orbital angular momentum and spin angular momentum. And here it's much more difficult classically to think about what we're talking about, because what do protons orbit? What do neutrons orbit? You can think of protons and neutrons spinning on their own axis. That is a classical concept you can think of. But the fact is that these are quantum concepts, and protons and neutrons have both L and S. And the total angular momentum of an individual nucleon, like a proton or a neutron, is equal to the sum of the orbital angular momentum and the spin angular momentum. These are vector quantities, but I'm keeping it simple at this point. And then the total nucleus spin, that is the spin associated with the entire nucleus, will be equal to the sum of all the individual total spins of each of the nucleons. Before we proceed, I need to just introduce you to the concept of parity, not for very long because we shan't dwell on this, we just need to get one thing clear and then we'll move on. If this is the wave function, remember that when you're talking about particles, subatomic particles, you regard them not only as particles but as waves. That's the whole point of quantum mechanics. And if it's a wave, then it has a wave function. That wave function has a value. This is distance, this is x, this is a value of distance. And what we say is that if the wave function has a value at a particular distance, x, then what you do is you look at the mirror image minus x. And you say if the wave function has the same value at minus x as it does at x, then the parity is said to be even, which sometimes is represented with a plus. Whereas if the wave function is minus the value it was at x, then the parity is said to be odd, and that's given a minus term. The relevance of all this, we're not going to go into any further detail. The relevance is simply that if the parity is even, then the L values are 0, 2, 4, 6 and so on. And if the parity is odd, then the L values are 1, 3, 5 and so on. And we'll come back to that a little later on. So then, we've been considering the smallest possible nucleus that has a nucleon-nucleon interaction. And we were looking at the deuteron, which is essentially heavy hydrogen, 2,1 hydrogen. It has just two nucleons, a proton and a neutron. And these are bound into a deuteron. And the binding energy we've already discovered is minus 2.225 MeV. Now the proton and the neutron will each have a spin. We're talking now about the spin angular momentum, the S value. And since each can be either up or down, you've got four possible combinations of spin. They can both be up. One can be up, the other down, or the opposite, one down, the other up. And then finally they can both be down. So what is the sum total of the spin in these cases? Well, here, remember the spin is a half. So here you've got half plus a half because they're both up, that's plus 1. Here you've got half minus a half, that's 0. Here you've got minus a half plus a half, that's 0. And here you've got spin down, so that's minus a half is minus 1. Now we've covered before the values of spin and what that means. Where the spin term is s equals 1, what that actually means is that there are three possible values for the overall spin of the nucleus. And they are 1 h bar, 0 and minus 1 h bar. Why are they like that? Because they go in steps of h bar, and that's the quantized step. We covered this in our quantum mechanics videos. So there are three possible spin states for a nucleus that has s equals 1. Whereas, of course, if you have s equals 0, then there's only one spin state, and that, of course, is at 0. If you have a nucleus with a spin state, total spin state equal to 0, then there is only one possible value that it can take. Now it's pretty obvious that as far as spin state 1 is concerned, this state represents the 1 h bar here, and this state represents the minus 1 h bar there. And the question you might think is, well, which of these two is this one and which of those two is that one? And the answer is, it doesn't work quite like that in quantum mechanics. In quantum mechanics, it's the superposition of these two states that represent these two here. The way it works is that the S1 zero state, that's this one here, is given by a combination where the two zero combinations are added together. So this one plus this one is the way we write it. That's in direct Dirac notation, which I've covered. That gives you that zero state there. Whereas the zero state when S is equal to 0 is just up, down, minus, down, up. And that is the zero state corresponding to here. So you've got 4 different states depending on the spin combination of the proton and the neutron in the deuteron. Now comes the key point. Experimentally, you can measure certain values of the deuteron. And what you find is that the total nuclear spin, that's I, that's the sum of all the J values of the proton and the neutron. So it's just the J value for the proton plus the J value for the neutron. That always comes out to be 1. The parity, which we mentioned earlier, remember, always comes out to be even, represented by the plus. And the total spin always comes out to be 1. Always. You never get S equals 0. And the fact that you don't get S equals 0 is the question I want to ponder here. Why does a deuteron have an S equal 1 state but not an S equal 0 state? And I'm going to speculate that it's got something to do with the nuclear potential that we were talking about earlier. So let's redraw that nuclear potential. It's a square well potential that we've been using. The potential is measured on this axis. This side is positive, this side is negative, and negative means attractive. So this is the binding, and the depth of the nuclear potential we calculated for the deuteron was 36 MeV. The potential goes to a distance which was R0, which for a deuteron is 2.1 Fermis, but of course ordinarily the radius or the extent of the nuclear potential is given by R equals R0 a to the 1/3, where a is the number of nucleons. So as the number of nucleons increases, this distance here will increase for the full nuclear potential. We also showed that the binding energy of the deuteron was minus 2.225 MeV and is therefore actually very shallow in terms of the depth of the nuclear potential. So you don't have to give very much energy to a deuteron to get the proton and the neutron liberated, no longer bound, free proton, free neutron. Now what I'm going to speculate is that the S equals 1 spin term, which we always find for deuteron, that is somehow contributing to the depth of this nuclear potential. And I'm also going to speculate that if you had an S equals 0 term here, the nuclear potential would not be as deep. Let us say that it's 36 MeV when it contains an element of the S equals 1 state, but that if, for example, it had an S equals 0 state, then the depth of the potential would not be so great. It would only come to, say, here. And if that were the case, then the binding energy wouldn't be so great. It would be there. But that would make it a positive binding energy, and a positive binding energy means the nucleus is no longer bound. So you wouldn't actually have a deuteron. So what we're speculating is that if you had an S equals 0 state, the depth of the nuclear potential wouldn't be so great, therefore the deuteron wouldn't be bound, therefore it wouldn't exist. And that's why you don't have S equals 0 in the nuclear potential for a deuteron. Well, if that's right, we can start building up our understanding of what we mean by this nuclear potential. The nuclear potential is some spherical term because that's what this is. This says that the nuclear potential extends to a distance r0. I've done this in one dimension. Obviously, what I'm alleging is that it doesn't matter which direction you go, whether you go in that direction, that direction, that direction, that direction, for a distance r0, the nuclear potential will extend that far. And of course that will also be in 3 dimensions, and in those circumstances a 3-dimensional shape would be a sphere. This is a spherical potential because what we're saying is that the nuclear force, the nuclear potential, extends to a distance r0 in any direction. That's a spherical potential. That's what we've been working with so far. What we're now arguing is that there is a spin term included in this that contributes to the depth of the potential, and that is why you only have an s equals 1 term rather than s equals 0 term in a deuteron. That is what we speculate. I now want to think about a magnetic moment. Better just define a magnetic moment for those of you who may not be aware of it. If you take a loop of wire and you pass a current through it, current I goes in that loop, and the area enclosed by the wire is A, then the definition of a magnetic moment is the current times the area. Simple as that. Obviously, when a current flows in a loop, it generates a magnetic field. That magnetic field will go perpendicular to the paper. In this case, I think I'm right in saying the magnetic field will come out of the paper, if I've got that right. It's essentially a 1-turn solenoid. That's all it is. And the solenoid produces a magnetic field. This is just 1 turn, so you will get a magnetic field, and you get a magnetic moment, which is defined as the current times the area. Now, you can think of an electron orbiting a nucleus. There's the nucleus. There's the electron. The electron is travelling at speed v, which of course is changing. It keeps an absolute value of v, but it changes direction. The radius of the orbit is r. We'll say the mass of the electron is m. And what we can say is the angular momentum of that electron. Well, angular momentum is ordinary momentum multiplied by the distance from the orbiting point. So the ordinary momentum is mv. Momentum is mass times velocity, and the distance from the orbiting point is r. So L is mv r. That's the angular momentum of the electron. The current is defined as charge divided by time. So that's going to be E, which is the charge on the electron, divided by the time, which is the time it takes for the electron to do 1 complete orbit, because every orbit it comes round again and you get more charge flowing. So you get a charge of E flowing every t seconds. The velocity of the electron is just the distance travelled divided by that time. The distance is just the circumference of the orbit, which is 2 pi r, and the time is the same t as here. So I can rearrange that to say that t is 2 pi r over v. So now I can substitute that t in here, and that gives me that the current I is E divided by t, but t is 2 pi r over v. So far, so good. Now, the magnetic moment is the current times the area. So, the magnetic moment for this electron is going to be the current, which is EV over 2 pi r from here, times the area, which of course is pi r squared. So the pi's go and one of the r's goes, and you're left with EVR over 2. So that is the magnetic moment of an electron which is orbiting the nucleus. We are being very classical here, of course. Now I'm going to multiply top and bottom by MVR over MVR. Right, so I can MVR over MVR is simply 1. And I can always multiply anything by 1. But MVR, of course, is, and the reason I chose it, is the angular momentum L. So that MVR, I'm just going to call L. This V and this R cancel that V and that R, and that gives me E times L, the charge on the electron, times the angular momentum, divided by 2 times the mass of an electron, is the magnetic moment. Now, Bohr introduced a concept, Niels Bohr, of the so-called Bohr magneton. And the Bohr magneton he defined as EH bar over 2m. So that's a definitional term. It's called the Bohr magneton. And on that basis, the magnetic moment of the electron is going to be, well, look at this. You've got the E over 2m part. That's here, here. So you just need, that's the Bohr magneton multiplied by L here. But you didn't need the H bar, so you divide that by H bar. And that now becomes the magnetic moment for the electron. The Bohr magneton, which of course is just a constant. Notice it's the charge on the electron times Planck's constant times twice the mass of the electron, that's all constant, multiplied by the angular momentum divided by h bar for an electron. And you won't be surprised to know that you can do exactly the same thing for a proton, even though classically the analogy doesn't work. And so that the magnetic moment associated with the angular momentum for a proton will be what's called the nuclear magneton times L over h bar, where the nuclear magneton is rather like the Bohr magneton. It's EH bar over 2m, but I'll put a little p there. What that means is E is the charge on the proton, which is of course the same as the charge on the electron, but just with an opposite side. H bar is the same, 2, and this is now the mass of the proton, whereas that was the mass of the electron. So very similar in concept. So this gives us the magnetic moment for the proton associated with the orbital angular momentum. Now you might also think that you could do these two terms in relation to not the orbital angular momentum, but the spin or angular momentum. So you might think that the magnetic moment of the electron, when it came to the spin, actually I'll put the equal sign there, when it came to the spin element would be the Bohr magneton times S over h bar, which would, as it were, be a mirror image of this here. Instead of L, you simply put S. But actually, that is not right. There is, in fact, a number that comes in front of this. It's actually almost twice as much. It's 2.0023 times the Bohr magneton times the spin divided by h bar. And that can actually be derived, though I'm not going to do so, from the Dirac equation. And you might think, therefore, that there will be a similar magnetic moment in relation to the proton for the spin term, and indeed there is. But it has a different value. In fact, whether it's the proton or the neutron, we usually say that it has a value g times the nuclear magneton times S over h bar. For the electron, g as it was minus 2.0023. For the proton, G for the proton is 5.585691. It can be measured to that level of accuracy. And G for the neutron is going to be equal to minus 3.826084. And why are they different from the electron? And why has a neutron got a magnetic moment anyway when it is uncharged? And the reasons for the differences, of course, is that an electron, as far as we know, has no structure. It is a fundamental particle. It is not made of anything smaller. It is just it. Whereas we know that a proton actually is made of quarks, 2 up quarks and a down quark. And a neutron is also made of 3 quarks, 2 down quarks and an up quark. And those quarks have charges. An up quark has a charge of plus 2/3 of the charge of an electron or a proton, and a down quark has a charge of minus 1/3 of the charge of an electron or proton. So 2 ups would be 4/3, minus 1/3 gives you a charge of 1 plus 1 for the proton, so that's where the proton's charge comes from, whereas 2 downs is minus 2/3, plus and up is plus 2/3, gives you an overall charge of 0. So that's why the neutron is uncharged. But look, inside these two, you have got charged particles. There are charges. It's perfectly okay to say that from a distance, the effect is that the proton has a charge of +1 and the neutron has a charge of 0. But that neutron has charges within it, and they, as they're orbiting, will create a magnetic moment. And that's why you get a magnetic moment for the neutron. It also explains why these are different, because you've got a different distribution of charges. Here you've got two lots of 2/3 and a -1/3. Here you've got two lots of -1/3 and one plus 2/3. So you're going to get a different value of G in the equation. So what happens if we want to know what the spin of the deuteron is? The combination of the proton and the neutron. Well, you might think that that will be the nuclear magneton divided by 2 times G spin for proton plus G spin for neutron. And that comes to the nuclear magneton divided by 2 into the two values I gave you before, which were for the proton 5.585691, for the neutron -3.826084. And if you add those two together, it's essentially 5.58 minus 3.82. The actual value is 1.759607. And that comes out to be, divide that by 2, 0.87980 times the nuclear magneton. But this value of magnetic moment for the deuteron can actually be measured experimentally. So if you do the experiment, you find that the value comes out to 0.8574 times the nuclear magneton, which is good. That's the theory, that's the experiment. Experiment always dominates. You always have to adjust your theory to accommodate the experiment, not the other way round. It's not a bad fit, but it's clearly not right. What has gone wrong? What have we assumed that we shouldn't? Well, of course, what we did is we assumed that there was a spherical potential. And a spherical potential is associated with the orbital angular momentum L equals 0. Maybe there is an L equals 1 or an L equals 2 term stuck in that potential. Well, here we come back to what we said before. There cannot be an L equals 1 term there, because the parity, remember, was measured for a deuteron as even. And if it's even, the values of L can only be 0, 2, 4, 6 and so on. So if there is another orbital angular momentum term in there, it has to be L equals 2. Since these are so close together, it's probable that we wouldn't have to go up to higher energies of L equals 4 and so on. So let's establish whether there could be an L equals 2 term in there. Well, what we would be saying is that the total magnetic moment for the deuteron, measured experimentally, would be equal to a proportion of L equals 0 plus a proportion of L equals 2. And of course, since those proportions must add up to 100%, that means that A plus B must equal 1. So effectively what you're saying is that the experimentally measured value, 0.8574, is going to be equal to A times the L equals 0 predicted value, 0.8798, plus B times the L equals 0 value. That gives us two equations, A plus B equals 1, and this equation here with two unknowns. I mean, for B you can simply substitute B equals 1 minus A. And you can solve then for A and B. And what you will find is that A comes out to be 0.96 and B comes out to be 0.04. From which we conclude that 96% of the potential is genuinely an L equals 0, a spherical potential. That's why the spherical potential is giving us good results, because at 96% it is. But there is a 4% contribution of an L equals 2 orbital angular momentum term. So from that we can now conclude that the nuclear potential is equal to quite a lot of spherical potential. Now we know that it must have a little bit of non-spherical potential, and then, as we speculated earlier, there is a spin term as well. So now we're starting to build up the component parts of the nuclear potential.